Hey everybody, thank you for stopping by the shop. Howie and I would like to wish you all a very Merry Christmas. I got my little reindeer here with me. This is a little Christmas special. I know people are hanging around the house on Christmas Eve and Christmas Day. So we're going to take a quick run over to my good friend Carl's for your entertainment and a little update on what's happening in his shop. Again, thanks for stopping by the channel, and I hope you all have a safe and festive Christmas season. Just to add a little bit more onto the start of this video, over at Carl's we're going to review toe jacks, a project that he's doing on a spin indexer, and then he's working on the oiling system on his Cincinnati Mill, and we'll be viewing that also. So it gives you kind of an update of what you'll be seeing here. Again, thanks for
Well, we're all
stopping
back
by
here
the
in
shop.
Carl's shop again, and I want to show you the latest project. I remember years ago when I first saw the Spindex indexing device, I thought that thing was built backwards. It just didn't look right, and I've used one for years and thought, this is a terrible piece of equipment. So one of the first things I've done, not first things, took me many, many years to get around to it, I turned a regular Spindex around so that the indexing is at the opposite end of the workpiece where it ought to be. And this was fairly simple. All it really required was making of this little dust collar, and then underneath the plate is a little spacer ring, and that was it. I made two parts, put them in, and then I bought this shaft collar, 1 3/4 inch diameter, bored it out to 45 millimeter, and then I drilled and tapped the index ring for a couple of 832, three 832 screws that are secured through the shaft collar. So basically it's the same design, it's just turned around backwards, and it looks good, it works good, quite simple and not a lot of work. But what really started this thing, remember I said it was many, many years before I got around to it, was a set of messages on the Home Shop Machinist bulletin board. A guy by the name of Jim, who goes under JHE 1973, took one of these Spindexes and added a regular index, a dividing head mechanism. Using a worm gear, dividing plates, and sector arms. Looks exactly like a dividing head. He put a lot of work into this and got me interested, and I decided I was going to make one of those, but I didn't want to use the regular index plate. I wanted to drive it with a stepper motor. So stepper motor is going to drive the worm, is going to drive the worm gear, and that worm gear is going to be bolted to the shaft collar, and that shaft collar is just simply going to be clamped onto the spindle. Now Jim threaded his spindle, and he used bearing lock nuts to secure everything up on his. And I got to thinking, you know, it's really a lot easier just to use a shaft collar. I tend to go for an easy solution. He used this gear set, a Boston 40-tooth gear, and its matching worm. I had this in stock. This is a 72-tooth gear and its worm. This was made by John Stevenson in England, and all the people who are on the Home Shop Machinist bulletin board will well remember him. He passed away this year. He was a very active member of that forum, and quite a machinist on his own right. So there will be more on the construction of this. I have the electronics that drive the stepper motor are complete, ready to go. I'll show that later when all this gets put together. So that's the next project. I'm working on it. Haven't quite figured out how to mount this stuff onto here, but we'll get there. Okay, next we're going to take a quick look at toe jacks once again. I told you a little bit about toe jacks in the previous video that Chuck and I made, and we thought it would be worthwhile going back and looking at them in a little more detail by themselves rather than as part of machinery moving. I move almost all of my machinery by myself. In fact, I can't remember if I ever really had help on any of the machines I've moved in here.
Hey, I've helped you.
Move them in?
Or out. No, I moved. All right,
Well,
go ahead.
Well, tell me, I've moved your machinery.
I know you have.
All right, guys. Anyway, I had a problem. And, you know, in the video on machinery moving, I showed you the various pry bars that I use. Well, the pry bars are wonderful, except when the machines are heavy and I have to use my 6-foot bar, or I think it's a 5-foot bar, and I can't at the same time push on the bar and get down on the floor and put my blocks underneath the machine. So this was a real problem, and one time I had to solve it. I had to get the machine inside, and I says, I'll make a toe jack. So this is my very first toe jack. It works. I'm going to tell you why I like it. I'll tell you why I don't like it. And first of all, it was simple. It was just a little bit of scrap steel stock, some welding, and a little bit of piece of 1-inch threaded rod, and it all screws together. The problem is that any design like this inevitably puts some force right here as this weight down here pushes the lifting bar into the cylinder. And what I did for that was I had a little piece of 1/8-inch Teflon that I inserted between the lifting bar and the cylinder to take up that force. The other problem, though, is that the ram on the hydraulic cylinder, this is a Interpack, a 10-ton, 2-inch stroke cylinder. The other force is taken between the ram and the this retaining ring in here. Now the retaining ring is just simply a piece of brass, maybe bronze, about 1/4 inch thick, and its inside surface, inside area, there's machined a 1/8-inch wide slot for the rod wiper. So there's really no surface area on this thing to restrain the force that's going out this way. It's just a very small surface. It was never intended to take a force in that direction. Interpack, in the design of this cylinder, wanted you to use only a vertical lift, no forces in any other direction. So this is an abuse of the cylinder. Quite frankly, it survived it. I've moved maybe, I can't say, maybe 4 or 5 machines using this, and it didn't destroy the ring. Okay, but the knowledge that it could has always led me to think I should redesign this and rebuild it to make a better toe jack out of this. Oh, and by the way, this is not the original cylinder that I used. This is a later one, and the original cylinder did not have this base plate. Of course, this base plate would interfere with being a toe jack. So what really started this project and got it going in its new form was Chuck's toe jack, and we're going to move down here and take a quick look at that. Now you've seen this before in one of Chuck's videos. It was copied from Interpack Design, and he reverse engineered it, based it around a jet cylinder, which is a little smaller in diameter than this. But the nice thing about this particular toe jack is that all of the forces are taken within these 2 pieces of tubing. There are no forces that are imposed upon the cylinder going this way or this way, so that there is no possible damage to the upper end of the cylinder. Oh, by the way, I didn't mention on the when we looked at the Interpack cylinder, was that at the bottom of the ram, where the seal is, there's just a pair of steel rings that are about, I think 5/16, maybe 3/8 inches wide, that retain the force down there. So they're just, as I said, the cylinder is not designed for anything other than a straight horizontal or straight vertical lift. So Chuck, you want to say anything about the design and build of this one?
Well, I love it that my good friend Tom Lipton tagged at China
yeah.
when I left him alone in the shop for.
Don't turn your back on him.
Don't turn your back on him. Again, it was all built out of scrap, copying the Interpack, and it basically uses your typical porta power Porta Power mounts onto there, and I just added slides on the tubing to make it tight, and pretty simple build. It was a fun little build, and it's been very functional, very good. So, and it weighs. We weighed it that last time. I forget. This is I think 25 or 30 pounds, and I think the inner pack, which is a bigger unit, is like 75 pounds, which would be something to lug around.
Yeah. So that was one of those, I got to have that moment. I says there are better ways than my original toe jack. And so Chuck donated the 2 pieces of tubing for this one. I had the toe and I had the base plate. It's exactly the same design, it's just I made it a lot shorter. I didn't have the quick connect for the toe, and in fact, as you see, these are spaced closer, and the reason for that is that they were machined in the wrong place originally. And so what you do when you make a mistake, well, you turn it into a design element. So that's a design element, it's not a mistake. But the design is the same. It has spacers to take up the difference in width at the front and at the back. And let's see, we'll take that off. It's got the standard inner pack collar, or well, maybe I'm not going to get that one out of there. But all else fails, get force. Well, I don't know.
It's machine too tight.
Yeah, maybe a little tight. But anyway, yeah. Buried inside there is a cylinder that's identical to the one I first showed you at the beginning.
And the connection is just similar to mine. The connection's there in the back. That's where the cylinder is.
Yeah, yeah. So the forces on this are taken, first of all, on this slide right here. That takes care of any wanting to move this way. Plus these shims pretty much secure the rising element in this direction. The forces imposed by the machine down this way want to rotate this inner element in this direction, and so that force is taken up between here and here, here and here. That's okay, it's not a problem. But what happens is, because the force, the overturning force going this way, is taken up on the back, that's a long ways away. There's almost 4 inches between here and here, and so there's actually 3 different shims in here that take up that force in this direction. When I finished this and connected the inner pack pump to it, you know, the hoses on those pumps are they're kind of stiff, and they're awkward to move around. You got to pick up both the jack and the pump. And I says, all right. There have been any number of builds of toe jacks based on regular bottle jacks. I says, let me try a bottle jack design and see what happens. So basically I took this design and I built it into a bottle jack. Well, you can't really, whoops, let me get that out of there. I forgot that was there. Can't really see the jack down inside. There is a bottle jack hiding in there.
Which you really kind of showed it in the last,
okay,
on the video.
Okay,
on the
good. They have that.
Yeah.
And anyway, I finished this. This is a piece of 5-inch tubing that I had in stock. This is a piece of a 5-inch, quarter-inch wall. This is a 4-inch, 1/8-inch wall. Actually, as far as I'm concerned, the wall thicknesses should have been reversed. I used what was available. And when I picked this thing up in the end, it's 29 pounds. I says, that's ridiculous. Honestly, and besides, I wanted to see if I could bring the location where the forces reacted a little closer together. I had another bottle jack, so here we go. One more toe jack. Do I need 3 toe jacks? No, but I got 3. So here's what I did. I started with this one. Been around for years. Never really found much use for it. Is this one stuck? Maybe we get some. There we go. So Now here's the sliding element. Here's a view of it from the front. And like the others, it's got some element that's constrained within a slot. In the one I just showed you, the toe itself went inside the slot, a much wider slot. In this one, what I did was I made a much wider toe, and it sits outside of the fixed element. And this surface provides the reacting location for the force in this direction, as the weight on here wants to rotate this thing in that direction. What I did to make this a little different was, rather than using tubing, I used channel, and that allowed me to react the force going this direction at the top within I think that's 5/16 inch of where this force is reacted. So they're very close together, and this made a much lighter design. This weighs 24 pounds versus 29 pounds, and that includes a somewhat heavier bottle jack. So there's my toe jack experiences. I'm keeping this one. I'm getting rid of the bigger one. That's going to a friend of mine who has a couple of heavy machines, and so all in all, it's been an adventure. Many thanks to Chuck for showing me his version of the Interpack design, and this has been a lot of fun. Okay, guys.
Well, and what we discussed about this is that this could be built with a drill press in a bandsaw.
Drill press, bandsaw.
There's really no machining. I mean, you don't need a mill and a lathe and everything to build this, which is kind of unique.
I bolted the jack to its base plate primarily just to keep it there. That took a vertical mill, and I had to make extended center drill, extended. I used an 8-inch drill bit to drill the hole down through here. I probably could have come around from the other side, but I wanted to spot the hole down into the base plate. I don't think the jack needs to be restrained. There are no forces on it. I originally designed it with just a little tab welded on here, so you could just set the jack inside a tab here and a tab there that would hold it in place. But like Chuck says, you could build it with a saw and a drill press, even a hand drill if you're really good at it. I sawed this slot and put it on the vertical mill and milled it. It doesn't have to be terribly accurate. You could saw this and just simply come back in and file or grind. You can use a little
disc grinder.
A little disc grinder, and just get that close enough that it slides freely. Doesn't need to be anything fancier than that. Yeah. Did have a little bit of fun making the handles. These were done on a Dacro bender, and drilled and tapped with a eye screws screwed in, and that makes just a nice little swivel handle. But you know, anything can be done on that. Bend them in a vise using strap iron. Drill a hole in the end of the strap iron and put the screws in, and there you go. So
cool. What are we going to take a look at next?
Oh, we're going to show the other current project real briefly. In the midst of all this, the project to put oiling system on the Taiwan mill was such a success. And as I told you when we looked at it a couple of times, that was kind of a warm-up for the real project, which was to revise the oiling system on my Cincinnati mill. And we're going to just take a quick look at the state of the mill. Kind of looks like an explosion of parts here in the workshop. And so hang on, we'll move over there and take a look at it. Well, here's the Cincinnati mill. It kind of looks like a machinery bomb went off because the parts are scattered all over the shop. So here is Cincinnati, and this is the ram, the table. It's a 9x42-inch table, same size as a lot of the Bridgeports. Behind is the table lead screw. It's a ball screw because this was a 3D contouring mill originally. All the 3D contouring stuff is long gone, and it's now used only as a manual mill. But these parts are pretty heavy, and they take a bit of work to get off. We'll show you just a little bit of that when we move into the other shop. as we said in the introduction to this, the purpose was to improve the oiling. This machine is a 1960s, I think, design. I don't know the the original owner. It came to me from an EDM shop, and they used it to make molds for EDM machining. And it was literally covered in graphite chips. We'll look at the saddle. The saddle was almost, in a minute, saddle was almost completely full of graphite. I had to take it down to a car wash and just spray it for half an hour to get the stuff out of there. And so the consequence of that is that the oil flow metering system was pretty well jammed up. And I've been hand oiling this for years, which is chancy at best. And I really wanted to put the oiling system back in. Cincinnati did a pretty nice job of it originally. So, Chuck, if you'll pan over here and we'll look at the saddle and the first part of the oiling system.
We'll go handheld.
Okay.
See what I'm seeing.
Yeah. Okay. We're going to start right here with the pump. This pump is built into the end of the saddle, and I'm not going to try to show you all of that. But the pump connected to this distribution block right in here, and then the excuse me, and then the oil goes. The metering units are out. Here are the metering units. If Chuck, you can go over here. These are a whole stack of metering units. They are basically an orifice that forms a resistance. And so we have a check valve built inside, and the multiple resistances in a parallel circuit, just like electricity, controls the amount of flow in each individual part of the circuit. And so one of these will go up here to the table way. Another one will go to, let's see, and I think the table ways, the dovetails are lubricated through these holes. Some of the channels go to they'll go to the underside of the saddle, to the knee saddle interface. Some of them feed oil to the lead screw. This is the crossfeed lead screw. And I said all of these metering units are plugged up, so they've got to go. What is not decided yet is whether I will put this back together exactly as it is, which puts the metering units inside the saddle and underneath the lead screw. So at any work that needs to be done on these, you at a minimum have to remove the table and its lead screw. I may elect to put them outside just like I did on the vertical mill, so everything's right out in front of you and quickly accessible.
Is it show the ball screw since we're over here?
Yeah. Okay, so Chuck's showing you the table ball screw. Oh, I got to tell you a little bit about that. One of the interesting things about this mill is that both lead screws are designed to be fed two different ways. There is you can feed them by hand through this gear, and someplace I can't show you all the details, but this gear turns the nut, and outside here was a hydraulic motor that turned the lead screw. So you can turn either one or the other, depending on what you want to do. And having taken the motor off, then I exclusively feed the table via the hand wheel and turning the nut. Very, very unusual system. And when I put it all back together, we'll show you it again. What it does is it groups all the controls at the front of the mill, and the table feed is not at the end of the table. It's roughly just a little bit beyond the middle of the table. It makes it a very, very ergonomically, I like that word, convenient machine to operate.
All right, let's go over to the other shop.
Yeah, we'll go back and take a look at that thing. Yeah, just real quick, just for giggles and grins, I'll show you the rest of the pieces that kind of fell off of the machine. Here is the milling head, just laying there. This is one area in which the Cincinnati is not as good a mill as the Bridgeport, and that is the head is not as well designed. I like the Bridgeport head. I use the Cincinnati, but it's not quite as good a head. And one thing, it does not have a power down feed. It only has a hand down feed via this hand wheel right here. Don't use it very often, just for boring. And I think the stroke on the on this, maybe just a little bit less than Bridgeport. I haven't really measured it. It does have a nose closed collet, does not have a drawbar, so there's a great big wrench that closes this nut. And back is the, let's see, Chuck getting over here. This is the turret and the ram dovetail right here. So that big ram we saw that with the label Cincinnati goes on here. And the turret sits on top of the machine base on the column, and we'll get to that in a bit. This is the motor mount. It goes on top of the milling head. And then if Chuck goes down this way, here's all the miscellaneous, the back of the DRO, the coolant tank sits on this. The DRO spars are here. Here's the coolant tank and a light and all kinds of junk like that.
And
okay.
So here's the base of the unit, right? That you've cleaned and painted.
Yeah. This thing gets a paint job. I don't think any of it's visible. This machine was professionally rebuilt maybe 15 years ago. Reground and turkited on the table and the saddle. The column weighs, as near as I can tell, this may be original Cincinnati scraping. I'm not certain of that, but there's no evidence that there has ever been any work on it, and these are just virtually as new. So I've never done any work on this, just left it alone. I said the turret, which we pointed at earlier, sits on top of this. And what else?
Yep.
Got a nice paint job.
Yeah.
Okay, here's the knee. And there's some interesting things about the knee, was that the oiling system was inside here. And literally, this is probably the most difficult.
Pardon my handheld here. Yeah, there we go.
Oh. This is probably the most difficult mechanical disassembly problem I've ever seen. It took me several hours to take 4 flow control units out and get the distribution bar junction block out of there. It's just an extraordinarily difficult piece of work, and the goal is I cut the old copper tubing and I extended it with new plastic, just like I used on the import mill. And so Chuck's wandering around the knee.
Right.
I think you saw earlier the hoist rings. Chuck will show you that. The hoist ring I bolted on each end. This allows me to pick up the entire knee and turn it over safely. There's absolutely cannot handle this weight by hand. It's all handled on the gantry crane, and where everything is under absolute control at all times. It can't possibly fall.
Can we get a peek in that window there? Is there
Sure.
anything to see in there?
No, not really.
Nothing really? Okay.
Not really. Maybe Chuck can show you, we'll do a panel of the, this is the big gantry. I showed you the small gantry used on the Taiwan mill build. This is the bigger gantry.
And that's unistrut up there.
Yeah,
Right?
that's an unusual unistrut. It's doubled and extra deep. I worked in a Fairchild semiconductor wafer fab one day, and they were building all kinds of structural elements out of that unistrut. And I told the journeyman that I was helping, I said, if you ever see about a 7 or 8 piece of that laying loose in scrap, pick it up for me. Next day he showed up with it, and I says, what? He says, I just walked over to the guys cutting this stuff and says, I need this, and walked away with it. Now you got to know Roy. He is 6'2", all muscle Irishman, and I guess nobody wanted to argue with him. But anyway, I got a 7 or so foot piece of heavy double strut, which I've used for. I think that's probably good for somewhere in the area of 500 to 7 to 1,000 pounds. Excuse me for stuttering there. A point load in the center, but I kind of keep it down if at all possible. Okay.
And then just looking beyond there, we're just going to take a high peek. Upcoming, you guys stand by. Someday we're going to get into Carl's sheet metals portion of the shop and look at the great amount of tooling he has for that, and maybe see some of the nice units he's built. All right, Carl. Well, thank you.
Alrighty.
Merry Christmas, everybody.
Yes, Merry Christmas.
This is coming out as a Christmas special, I hope. Howie. 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 Come here. Good boy. Come here. That's a good boy. That's a good boy. Okay. Turn around. Turn around. All right, Howie. Let's go. Let's go eat some dinner. All right. Down. Down. Good boy. Oh, you're a good boy. Yeah. Oh, you get itchy. Okay. Oh. Okay. 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 Thank you. Thank you. Thank you. Okay. Go. You go now. You can go now. You're done. You can go now. You can go now. Thank you. You want to sit down?